Okay, we have a couple problems using the counting rule formulas. The first one, it says an application for the counting rule for combinations. At our last business meeting, there were 15 people who attended. One of the action items was to establish a 3-person committee that would be in charge of refreshments for the upcoming annual budget meeting at the beginning of the year. Although people were asked to volunteer, nobody did. It was then decided that everyone would write their name on a piece of paper and put it in a box for a drawing. There would be 3 people drawn from the box to serve as the volunteers. Janet and her friends Judy and John were among the 15 people attending. Janet wondered what the chances were that all 3 of them would be chosen. Now in this situation the order is not important. A committee with Janet, Judy, and John is the same as a committee with Judy, John, and Janet, or Judy, Janet, and John, etc. We will use the combination formula. Now the formula involves factorials, and the notation here is we're taking a combination of n items, choosing n, little n, at a time. And some notation. We'll see this notation again later as we go into sampling towards the end of the course, so it's a good idea to kind of think of how this formula works. But what I have in this situation is to identify the total number of people, and here would be 15, and they are choosing 3 at a time, so that's my value for little n. So I have a combination of 15 choose 3, and that would be 15 factorial over 3 factorial times the quantity of 15 minus 3 factorial. Okay, I'm going to do a little bit of simplification here in this next step. That'd be 15 factorial. 3 factorial is 3 times 2, and 15 minus 3 is 12 factorial. Now, many times you can get a lot of cancellation. 15 factorial is 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8. In other words, 15 times 14 times 13 times 12 factorial. And I stopped there because I have a 12 factorial in the denominator that will cancel with it. And then I still have the 3 and the 2. So getting a little bit of cancellation, I have 3 goes into 15 5 times, and 2 goes into 14 7 times. So we end up with 7 times 5 times 13, which is 455. So the probability that all 3 of those friends are chosen for that 3-person committee would be 1 out of 455, and that would be 0.0022, or about 1/5%. So it's not very likely that the 3 friends there would end up on that committee. We've talked about probabilities already in this section, and we can see on simpler examples that it's very important to know how many outcomes are possible for a process. And those outcomes, the number of them or what they are very important in ultimately calculating probabilities. So at the beginning of a probability problem, we need to establish what the process is and make sure we've well defined it. In other words, in statistics and probability, they would call it then an experiment. And then it becomes important to be able to do some counting sometimes. Sometimes it's easy, like rolling a die. You know exactly there are 6 possibilities just based on your experience. But here in this situation where we have people being chosen out of 15, 3 at a time, what are all the possible situations there? Sometimes we do have to rely upon formulas to do the counting for us. Now our next problem involves permutations. It says many states design their automobile license plates with space for up to 6 letters or numerals. If a state decides only to use numerals on the license plates, how many different license plate numbers are possible? And in that situation, order is important. Unlike the previous problem, the order in which the numerals or letters ultimately will appear on your license plates is important. They should be counted separately. And how many possible combinations if we just use numbers? In this particular case, it's not hard to think of this as maybe even a tree diagram. I have 10 possibilities for the first place. I have 10 possibilities for the second. 10 possibilities being from 0 to 9. 10 possibilities for the third, the fourth, the fifth, and the sixth. Multiplying them all together, I'll just have 10 to the 6th power, and that will be 1,000,000 possible license plates that can be made just with numerals. Now, what if we want to increase the number of possibilities by making the first 2 places of the license plates use letters for those? So just on the first 2 places, I'm going to use letters. And what are the possibilities for using letters for those 2? Now here's where order is important. It will matter as to what order I put the letters in. I'll also only use 24 letters since the letter O and I look too much like a 0 and 1. I won't use those. So I have 24 letters, and I'm going to take 2 of them at a time and put them into those first 2 slots on the license plate. Order being important. In that case, I would consider this problem a permutation, and I'm going to use the permutation formula of 24 letters 2 at a time. And plugging into the formula, I'll have 24 factorial over the quantity 24 subtract 2 factorial. And then I get some really nice cancellation here. 24 subtract 2 is 22. So I'd have 22 factorial in the denominator. 24 factorial in the numerator is 24 times 23 times 22 times 21 all the way down to 1. So really I just have 24 times 23 times 22 factorial, and then that will cancel with my 22 factorial in the denominator, and all I'm left with is 24 times 23, which works out to be 552 possible permutations of those 2 letters. Now, with 552 possibilities for the first 2 slots, then the 3rd slot, the 4th slot, the 5th slot, and the 6th slot all have 0 to 9. I will just multiply the 552 times 10 to the 4th and end up with 5,520,000 possible license plates. A state, of course, that has more licensed drivers would want to increase their use of letters in the license plates. Well, I hope this helps, at least gives you an idea of how the formulas work. Use the course help forum to ask questions or send me an email. Thanks.